Hello, and welcome to this recorded learning about the Spartan-6 clocking resources. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the clocking generation capabilities in the Spartan-6 FPGAs, including its new DCM functionality. It also explains its global and I/O clock routing resources. This module also provides some recommendations about getting the most out of these clocking resources. Spartan-6 is an unusual FPGA architecture. It contains some of the features of Spartan-3 and Virtex-6 device families. It is still a low-cost device family, but has some of the newest features in the FPGA industry. In this module, we're going to describe the global and the I/O clock networks in the Spartan-6 FPGA. We're going to describe the clock buffers and their relationship to the I/O resources, and describe the DCM capabilities in the Spartan-6 FPGA. Note that this module does not discuss the PLL functionality, which will be necessary to you, so please refer to the Spartan-6 user guide to learn more about the PLL functionality. Spartan-6 has two different clock networks, global and I/O clock networks. Spartan-6 does not include regional clock networks like Virtex-5 or Virtex-6, which is a notable difference if you're used to working with those device families. The global clock network supports up to 16 global clocks and provides performance up to 400 MHz. The Spartan-6 I/O clock network is used for distributing clocks to the IOB resources, which contain the SerDes functionality and operate at very high speed, in this case over 1 GHz. There are 4 I/O clocks per half edge and 2 I/O clocks that span the entire edge of the device. Spartan-6 also includes 2 DCMs, that is, digital clock managers, and 1 PLL, that is a phased lock loop, per clock management tile. The clock management tile is commonly referred to as a CMT. The DCMs are a combination of analog and digital technology. The DCMs are used to remove the input delay of a clock brought into the FPGA as well as for clock generation. The PLL does not provide division capability, fine phase shifting, or complementary outputs. That is all accomplished with the use of the DCM. This module will introduce the DCM functionality, but unfortunately we don't have enough time to discuss the PLL features. To learn more about the PLL features, please consider attending the Designing with Spartan-6 and Virtex-6 FPGA device family course, or refer to the Spartan-6 user guide. Spartan-6 is a wire bond type device. This means that the I/O pins are distributed around the periphery of the die. This implies that each pin is associated with an I/O bank on the perimeter of the device, like the Spartan-3 device family. But unlike Virtex-5 or Virtex-6, which have I/O banks placed in columns throughout the FPGA. This also places some restrictions on clock input pins. Spartan-6 has 8 global clock input pins per edge of the device. The global clock pins are really more like clock-capable I/O pins, which are regular I/O pins with special routing resources that allow the input clocks to get to the CMTs, that is the clock management tiles, which are located in the center of the die. Most of the CMTs are in the center column of the die, a long way from the I/O pins. The global clock input pins are the only pins that should be used for clock inputs. That means that the clock input pins should be used for both global as well as I/O clocking. Now there are no dedicated I/O clocking input pins. Each clock input pin can be used as a single-ended clock input with the iBufG primitive used for instantiation. Adjacent dedicated clock input pins can be used for differential clock input pins with the iBufDS primitive used for instantiation. The global clock pins number 2i and 2i+1 is the adjacent pin pair. As an FYI, if you don't use the dedicated clock pins for clocking, you can use them for regular I/O as well. The pins can support any I/O standard that is compatible with the I/O standards used in the same bank. This is required as part of the I/O banking rules. These rules require that input pins share the same power supply in a single bank, and that output pins share the same power supply in that bank as well. To help with planning your I/O pin layout, I recommend that you listen to the Architecture Wizard as well as the Pinahead REL. When using the smaller density Spartan-6 devices, there is 1 I/O bank per edge. You should also note that the global clock pins are in the same I/O bank. even in the larger densities, so pay particular attention to this when planning your design pinout. Global clock networks can distribute a clock to every synchronous element in the device. This includes registers, block RAM, DSP slices, cores, I/O blocks, clock dividers, and SerDes resources. The dedicated clock pins allow for the input clock to route to the center of the device where the CMTs or clock management tiles are located, and then connect to the dedicated global routing resources, which are accessed with a BUFGMUX primitive. This allows the clock to distribute throughout the die, effectively on a big fat wire. While technically Spartan-6 devices have clock regions, it is not as important since all 16 global clocks can enter all clock regions. We will see that there are a couple of places where the clock region concept might still matter. Like Vertex-6, the clocks are routed vertically through the center spines, then connect horizontally to horizontal clock rows called BUFHs, which are at the intersection of the vertical spine and the horizontal clock rows. The BUFH primitive does not support a clock-enable functionality, so it is simply just a buffer. The global clock routing resources can drive either a clock or a reset port on every synchronous element in the device. This allows it to distribute a global reset signal. Note that driving more than one global reset signal on a global clock network is not recommended in Spartan-6. Also note that global clock networks cannot reach any other ports on the FPGA synchronous elements. That is, they cannot drive the clock-enable inputs of the slice or data inputs of LUTs. This slide shows you a representation of the intersection of the vertical spines with the H-clock rows. As you can see, the H-clock rows are basically an extension of the global routing resources. Each of these 16 2-to-1 muxes can be configured to take its input from a CMT or the vertical spine, which would come from a dedicated clock input pin. Each H-clock row is either adjacent to the PLL or both DCMs in a single CMT. Direct connections from the CMT allow for more than 16 clocks per device. To connect a CMT output directly to an H-clock row, you will need to instantiate a BUFH clock buffer. This is a simple buffer with no attributes. Just connect the I port to the desired DCM or PLL output and use the O port as a clock signal. Clocked elements connected to that clock will then be restricted to one row. Using the direct connections from the CMT to the H-clock rows can be complex and should only be used when it is necessary to access more than 16 clocks. The BUFH instantiation is required here, but is not recommended in any other context. This is because the BUFH is only partially supported in the Spartan-6 FPGA. At the bottom of the slide is a representation of the vertical spine inputs. As you can see, there are 48 inputs available to the vertical spine. 16 inputs from the left and right edge of the die, 16 inputs from the top and bottom edge, and 16 inputs from the CMTs and/or internally generated from the FPGA logic. In the end, understanding this is not significant, but it does show you the possible sources of clock and reset signals that you can have. Each global buffer, that is a BUFGMUX, has an associated 2-input multiplexer that drives the output onto a global routing resource. These inputs are configured to possibly connect from global clock pins on particular edges of the die or from the BUFIO2 buffers, which are designed to distribute your high-speed I/O clocks. The I/O clocks are designed for low fan-out and maximum performance. This will multiplex 2 clocks together and then drive the result onto a global routing resource. The I/O input can be driven directly by one of the 2 global clock pins. The top BUFG can be driven by one on the top edge and one on the right edge. The bottom BUFG, one on the bottom edge or one on the left edge. The I1 input can be driven from a second set of pins on the same 2 edges. Either input can be driven by a BUFIO2 output. So the top BUFG will support 2 BUFIO2s on the top edge and 2 BUFIO2s on the right edge, and the bottom BUFG will support 2 BUFIO2s on the bottom edge and 2 BUFIO2s on the left edge. The BUFIO2 routes add extra delay onto the clock path. The BUFGMUX can be driven from a DCM or PLL output as well, and the BUFGMUX can be driven directly from the fabric logic if so desired, but the phase of the resulting clock is not controlled. So again, note the BUFIO2 will add extra delay on the clock path when it is used in this fashion. The BUFGMUX can also be driven from the DCM or PLL outputs or from the FPGA fabric, but note if you're deriving a clock from the fabric, its phase is not controlled. What all this means is that knowing how the various possible inputs can connect to the BUFG MUX may be helpful if you are distributing a large number of clocks. But frankly, I think it is easiest just to build the clocking structures into your design and then let the tools decide how to group clocking resources to the BUFG MUXes. For more information on the BUFIO2 cell is given in the I/O clock resources lesson of this module. Likewise, if you're still curious about all the possible connections to the inputs of the BUFG MUXes, please refer to the user guide. Every BUFG MUX also provides a synchronous switching functionality. This is done by changing the S input, which allows for a glitchless switching of the output. If you're going to use this feature, try to place the clocks to be switched onto the same edge. Again, if you are confused by the discussion of the mapping of the clock pins to the BUFG MUX inputs, refer to the user guide for more discussion. If you would like to have an implementation be asynchronous, that can be accomplished by using the clock select type setting of asynchronous. The BUFG MUX also supports a standard clock buffer instantiation. This is simply a routing of a global clock onto a dedicated routing resource. The BUFG MUX also supports a BUFG clock enable primitive, which supports a clock enable functionality. This allows for glitchless gating of the clock. The clock enable functionality saves the user from distributing a global clock enable throughout the device. In this case, the clock enable input must be synchronous to the non-gated clock. Generally, this means that the clock enable is derived by FPGA fabric running on a global clock sharing the same input clock. Now note that all three BUFG clock enable, that is the BUFG, and the BUFG MUX primitives are explained in the Xilinx Unified Library of Primitives, and this is available at support.xilinx.com for more information. Now in this slide we want to get into why the DCM and PLLs exist in the FPGA. The answer is simply a clock insertion delay. You see, clock insertion delay moves the sampling window of inputs. The clock insertion delay will increase the clock to output time of outputs, as well as the clock insertion delay is voltage and temperature dependent, and increases require the setup and hold time window. The clock insertion delay can include a global clock input delay, routing to the BUFG from, say, the edge to the center of the die, delay of the BUFG itself, or the delay of a global clock tree to the back to edge. And clock insertion delay is significant, and it should be noted, of course, it's included in the timing analyzer. Now, all of these delays can be compensated with the use of a DCM or PLL, and fortunately, Spartan-6 has a number of clock management tiles. Now, this is an example of how to remove clock insertion delay in a standard system. In this case, a DCM or PLL is going to be used to deskew the clock, that is, remove that clock insertion delay. First of all, the clock will come in through an iBUFG primitive and connect to a BUFIO2 primitive, which will be the fast way to get that clock to the PLL or DCM. Then that output clock will be routed on a global buffer, and at one point will be fed back through a BUFIO2 feedback. The BUFIO2 to PLL DCM path will be matched to the BUFIO2 feedback to PLL DCM path. This will allow the PLL DCM to keep the in and the feedback in inputs in phase. Therefore, inputs to the BUFIO2 and the BUFIO2 feedback will also be in phase. And this results in no clock insertion delay as measured at the I logic and the IOB. Now please note the BUFIO2 and the BUFIO2 FB should be inserted automatically by the implementation tools. This slide is trying to show you how I/O clocks are handled by Spartan-6. These I/O networks only drive the IOBs on the periphery of the die. Specifically, they drive the iLogic/O logic resources, which are your high-speed SerDes resources. I/O clocks can come from global clock pins via the BUFIO primitive, or they can come from the clock management tile, that is the CMTs, via the BUFPLL primitive. Now there are 4 I/O clock networks driven by the BUFIO2 drivers in every half edge. That is a total of 8 groups of 4, or 32 for the whole device. There are also 2 high-speed I/O clock networks driven by the BUFPLL drivers on every edge, for a total of 4 groups of 2, or 8 for the whole device. In the end, it does not really matter how many possible inputs you have, since the tools will decide the connections to the I/O logic. But the key is to understand the difference between these two primitives. BUFIO2's input come from the global clock pins. The BUFPLL's input come from the CMTs. Also, please note there are additional dedicated high-speed I/O clock networks that are used exclusively by the integrated memory controller, which we're really not going to talk about here. And as you may or may not know, Spartan-6 contains a dedicated programmable memory controller on the device. The BUFIO2 is designed specifically for the use with the I-SerDes and O-SerDes resources. In addition to driving the I/O clock output onto the I/O clock network, this buffer can also generate a divided clock and chip enable required to manage the data transfer within the I/O-SerDes resources. These are located in the center of each of the 4 edges. The input I will come from the global clock pins or the GTP clock output pins on the same edge, and that would of course be coming from the MGTs or serial gigabit transceivers. The I/O clock output will drive the I/O clock network for clocking the I/O logic and the high-speed clocks of the I/O-SerDes. The divided clock or div clock output drives BUFG or CMTs in the center column. The frequency is divided by using the divide attribute that is associated with the BUFIO2 primitive. It's intended to drive the clock div input of the I/O-SerDes, among other things. We'll see this a little later on. Likewise, it also generates the SerDes strobe output, which drives the I/O clock enable of the I/O-SerDes resources. This is asserted for one I/O clock period out of every divide to transfer data from the I/O clock domain to the div clock domain, or vice versa, depending upon the use of the SerDes. Timing of the SerDes strobe ensures maximum time for clock crossing. So again, note the GTP clock output pins are the output clocks of the GTP transceivers. We're really not going to get into the transceiver functionality here in this module. And the SerDes strobe, which is intended to be connected directly to the I/O clock enable input of the SerDes, determines which rising edge of the I/O clock should be used to launch capture data going to or from the div clock domain. The div clock output of the BUFIO2 has a dedicated connection to the center column of the chip where it can access the BUFG and the clock management tile resources. This slide is trying to show you the association of each global clock pin with the BUFIO2 inputs associated with each I/O bank. As you can see, each I/O bank has 8 global clock pins associated with it, and each pin has a pre-assigned PN pair in case you want to bring in a differential clock signal. Each global clock can drive more than one BUFIO2 on each half edge. Each BUFIO2 on each half edge only drives the I/O clock network on that half edge. However, each global clock can drive the I/O clock networks on both half edges. That is why the twists in this diagram represent the flexible connection between a fixed global clock pin and its connection to the available BUFIO2 buffers associated with the 2 half edges. In this way, a single clock input pin can drive one BUFIO2 in each half edge. Each BUFIO2 can route an input clock through 3 different dedicated paths. The I/O clock output routes directly to the I/O clock network. The div clock output, if used, can route to either a BUFG or route to a clock management tile. Now, I know you may be swimming in too much detail right now, but this information is really just to explain what you can do. When we get to some of the use cases, the reasons for these possible uses will make it a little more easier to understand, and it'll make more sense a little later on. In this slide, we're trying to describe how the I/O clock resources can be used in a single data rate application. So in the case, the BUFIO2's divide capability allows it to be set to the same value as the data width attribute of the I/SerDes primitive. The high-speed source clock comes into the FPGA through a dedicated clock pin and then gets divided down. It then can be distributed globally on a global routing resource, or BUFG. The div clock can also be used for the clock divide input to the I/SerDes 2 component. Note that the BUFIO2 also generates the SerDes strobe for the I/O clock enable input to the I/SerDes 2 block. In this case, we have a high-speed data signal coming into the FPGA that is accompanied by a double data rate clock. So to decode this data, the high-speed clock must first come in through a dedicated clock pin and be used to generate 2 I/O clocks, one for clock 0 and another inverted for clock 1. As you can see, this requires 2 BUFIO2 primitives, the top to divide down and be distributed on a BUFG to the FPGA logic. The other will be inverted and driven to the clock 1 port of the I/SerDes 2 component. Note that the first BUFIO2 requires the use of the doubler or use doubler attribute to be set to true. Recall that the BUFPLL is designed to take a clock generated from a clock management tile and route it on the I/O clock network. The BUFPLL is designed specifically for use with the iSerDes and OSerDes resources. Like the BUFIO2, it generates the I/O clock output onto the I/O clock network and also generates the chip enable required to manage the data transfer within the I/O SerDes resources. Unlike the BUFIO2, it does not generate the divided clock. The divided clock should come from the same PLL that generates the high-speed clock in this case. The global clock input to the BUFPLL is the low-speed clock coming from a global clock network via a BUFG. This should not be confused with a global clock pin. So I want to be clear on that. This is not referring to a global clock pin of the FPGA, which is a clock-capable input pin. Note that in devices with 6 clock management tiles, the BUFPLL can only be fed by 4 of the 6 PLLs. For more information about this, I encourage you to check out the user guide. In this slide, we have an example of a clock-forwarded output for a double data rate application. And in this case, we're going to use the clocks generated from a PLL as well as a BUFPLL to generate a high-speed clock-forwarded output interface and do this relatively easily. So first of all, the PLL on the left will generate the high-speed clock, and this must run at the bit rate of the data interface. That is, if it's single data rate, the DDR would not be supported in that case. The PLL will also generate the low-speed clock for driving the user logic and the clock div, which will be driving to the BUFPLL. In this case, a DDR clock for forwarding is generated by sending a combination of 1010 to the lower SerDes resource. The BUFPLL in this case aligns the I/O clock to the global clock and then generates the SerDes strobe required for managing the data transfer in the I/O SerDes resources. Internal to the FPGA, the high-speed clock must be single data rate. The high-speed clock must run at n times the low-speed clock, where n is also the data width of the OSerDes, used both for clock and data. The data OSerDes sends the high-speed data. The clock OSerDes, this is the lower SerDes block in this example, sends that fixed pattern of 1010, thus making one transition per bit period. This is a double data rate clock associated with that interface. An interface generated in this manner can be easily received by an FPGA using the clocking described for receiving a high-speed double data rate interface. For higher serialization rates, up to 8, each output SerDes can be cascaded with an associated slave output SerDes. The outputs can be implemented using any I/O standard, but for higher data rates, it is common to use the differential I/O standards such as LVDS. When high-speed data is brought into the FPGA along with a phase-related low-speed clock, we're going to build a clock-forwarded input interface just like this. And in this case, we're going to use the PLL to generate the high-speed clock and then use the BUFIO2 feedback to match the phase to the incoming low-speed clock. In some interfaces, the clock is sent at a much slower rate than the data, such as a divided clock is sent instead of a high-speed clock. The edges of the divided clock are used to provide the correct phase for sampling the high-speed data signal. For this interface, a PLL is required to multiply the frequency of the incoming clock. However, the phase of the high-speed clock must match the phase of the incoming clock for data sampling in the I/O SerDes resources. In this case, the PLL keeps the clock in and clock feedback in phase. Because the BUFIO2 to PLL path is matched to the BUFIO2 feedback to PLL path, the two clocks are in phase of the inputs of the BUFIO2 and the BUFIO2 feedback. Thus, the phase of the high-speed clock is locked to the phase of the incoming clock and is correct for sampling the input in the SerDes resource. Using the clock feedback equal clock out 0 enables the divide by m divider on the clock feedback in input, thus resulting in the frequency of the input and feedback clock being the same at the input of the phase detector, because clock in is a low-speed clock and clock feedback in is the clock out 0 output, which is the high-speed clock. Now, let's take a couple of minute break and give you a chance to verify you've learned a few things with a short quiz. Now that we have covered the I/O clock network, global writing resources, and the dedicated clock input pins, we want to introduce the contents of the clock management tile. The CMTs are located in the center column of the die, and each Spartan-6 device contains up to 6 CMTs, depending on your device density. The DCM is a digital delay lock loop. It provides the most clock building functionality and compensates for the input delay associated with routing an input clock to the DCM. Each CMT also has an associated PLL that reduces the internal clock jitter and conditions an input clock by removing the input clock jitter. The PLL features are described in the user guide and will not be discussed further in this recorded e-learning. CMTs are located in the center column of the FPGA. The DCM inputs, though, we want to note, are slightly restricted to certain BUFIO2s. So, for example, the clock in can be fed only by the ones located in the same half of the die, that is, the top or the bottom. That is, a DCM on the bottom can be fed by all 8 on the bottom and the bottom 4 on both sides. The clock feedback can be fed only by the ones located in the same half. Likewise, the PLL inputs are also slightly restricted to certain BUFIO2 elements, so that the clock input 1 can be fed by the ones in one quadrant on the same half, that is top or bottom of the die, and the clock feedback can be fed only by the BUFIO2 feedback located in the same half. That is, the clock in 1 of a PLL on the top can be fed by the 8 in the top left quadrant, and the clock input 2 can be fed by the 8 in on the top right quadrant. Now also, the CMT outputs can drive the BUFGs, or must drive the BUFGs, in the same half of the die. So the sources for the clock input 1 and clock input 2 ports of the bottom PLLs are opposite to those of the top PLLs. That is, the clock in 1 can be sourced by the bottom right quadrant, and clock input 2 can be sourced by the bottom left quadrant. Now, if you don't do anything, the tools should automatically swap the clock input 1 and clock input 2 ports if necessary. Now this slide is trying to show the most common configurations of the clock management tiles. The grouping of the 3 elements in each clock management tile, again recall 2 DCMs and 1 PLL, is meaningful. Within each CMT, the DCMs and PLLs can be cascaded together through direct local connections. And there are really 3 primary configurations, as we can see from this diagram, that most customers use. First of all, the top one, configuration 1, is very common in the sense that all 3 clocking elements, that is 2 DCMs and 1 PLL, can be used independently for whatever purpose. Configuration 2, the PLL can be used to condition an input clock jitter before passing the clock to one or both DCMs for clock generation functions. And in the bottom example, the PLL can take a single DCM output clock and create an ultra-low jitter version for global clock distribution. And this is commonly done when a designer is using the clock FX output of the DCM. It is expected that the second option will be especially useful. In this case, the PLL can accept a much wider range of input frequencies, duty cycles, and input clock jitter than the DCM. Using the dividers, jitter filtering, and duty cycle correction in the PLL allows the resulting clock to be fed to the DCM, which can then perform its further clock functions. In the past, these functions may have been required to be done using external PLLs on the PCB board. Now, these functions can be pulled, and really should be pulled, inside the FPGA since you're already paying for a number of dedicated PLLs. This will save you PC board space and cost, of course. Also note that either DCM in the CMT can be cascaded with the PLL, so there's routing flexibility there. There are 2 configurations for every DCM. The SP supports phase shifting and many clock generation capabilities. The clock gen primitive is for generating clocks and does not support phase shifting. All DCMs can be configured as either primitive. The DLL's clock input can be between 5 and 250 MHz, although since the DCM can be multiplied by 2, it effectively supports frequencies up to 500 MHz. The DCM deskews clock inputs by compensating for the input delay. Now we'll talk a little bit more about this in a minute. The DCM is also used frequently for correcting duty cycles to 50-50, which is available on certain outputs. The DCM supports a static phase shifting functionality that can be fixed to a fractional increment of 1/256, the input clock period. It also supports a dynamic phase shifting feature in increments of the DCM's tap delay. But the most commonly used feature is the digital frequency synthesis, or DFS, which operates from 0.5 to 333 megahertz. This allows the designer to select and multiply and a divide with the desired clock. So the M, or multiplier, and D, divisor range will vary by the configuration of the DCM, which is dependent on the combination of features that the user selects. And this is usually especially affected by the output frequency that the customer desires. If you've used the DCM before, you should note that it is no longer necessary to specify a low or a high frequency mode for the DCM. In the case where a customer is, of course, using the architecture wizard to customize their DCM component, then the DCM will automatically be customized based on the frequency the user specifies with the architecture wizard. So, in effect, very little thinking has to occur by the user in the customization. This slide tries to explain how clock deskew is performed and realistically why we care about it. First of all, a DCM works by inserting delay on the clock net until the clock input rising edge is in phase with the clock feedback rising edge. So the first thing I of course want to point out is, again, this is a digital implementation. There is no PLL in this circuit, as you can see. But in this case, the delay is implemented via a series of delay elements. So as you can see, we have all these programmable fixed delay elements, and depending upon your device family and speed grade and all, they'll have a various length delay element. What will end up happening is the clock input will be going through these delay elements, and then the phase delay control will select with that multiplexer which of those phase shifted outputs to use. That'll be fed back on a global routing resource, or in this case denoted by a clock distribution network, and then that feedback will come back in and compare to the input, and then based on the difference, or the phase difference between the clock in and the clock feedback, then a different delay element will be selected. Now note, what this effectively will force is that a delay element on every sample will phase shift by a fixed amount, moving over one way or the other, but depending upon that comparison between the clock in and the clock feedback. So what we'd like to point out here is, again, using a digital implementation, there is always going to be a fixed amount of constant phase shift that can occur. And there's no way to predict whether it'll be forward or backward on every sample. The generated clock has all the same attributes, including a frequency and jitter. These adjustments will create additional jitter on the output clock. So one important thing to be aware of is that the synthesis and the implementation tools should automatically calculate and adjust for this extra jitter during timing analysis so that your system can tolerate that. But I'd like to point out as well, though, that again, being that this is a digital implementation with a fixed jitter, not all telecom applications can actually tolerate the jitter. So it's important, if you're not certain, to check your actual data sheet or user guide and make certain that the jitter characteristics of the DCM and what you select with the architecture wizard are compatible with your circuit. So as we just discussed, the delay lock loop, or DLL, will implement your clock deskewing, thus matching the phase of the clock in and the clock feedback ports. This can be used for clock insert delay removal, zero delay buffers, or for building clock mirrors. It also will make available a duty cycle corrected 50/50 output based on certain outputs. So one of the things I'll point out is check your user guide to find out which of your outputs will be 50/50 duty cycle corrected. All DCM output clocks have a fixed phase relationship with clock 0. So there's a clock 90, clock 180, and clock 270 phase shifted outputs automatically available. Likewise, there's a multiply by 2 and multiply by 2 phase shift by 180 that is also available to you if you would so desire. You also have a programmable clock divide, and this will divide your clock input by some number integer results as well as small fractional results, so you can divide by 1.5, 2, 2.5, 3, 3.5, etc., all the way up to 16. So again, to find out all the complete values, you can either go to the architecture wizard and try and build it and see what values are available to you, or go to the user guide. Now likewise, as I mentioned, the clock FX and the clock FX phase shift 180 are your digital frequency synthesis outputs. These offer a wider range of frequency generations that are available by the clock divide. But the caveat is with the clock FX is the jitter characteristic can be excessive depending upon your application. So what I tell people always to do is to verify when they create their DCM component to go ahead and select the clock FX, build the clock FX they want, and then use the jitter calculator that is available in the architecture wizard. But in general, if you already know that the clock divide supports a division you may want, then go ahead and use the clock divide. That's going to have a better jitter characteristic than the clock FX. Now, as I mentioned, the resources here in the DCM also support phase shifting. So you can phase shift all clock outputs when you customize the phase shift resources. But all clock outputs will retain their phase relationship to the clock 0. Now, there are a couple different modes to choose from with your phase shifting functionality. You can use none so that clock in and clock feedback are kept in phase. You can do a fixed phase shift by specifying a value from -255 to +255, and this will be done in increments of 1/256 of the clock period. Or you can do a variable phase shift, so the clock in and the clock feedback phase can be changed dynamically. This will shift the amount to be changed by using a special DPS interface. So to learn a bit more about that, check that user guide to learn more about that. We just didn't have enough time to cover all the functionality. This can be increased or decreased step by step, and the variable steps are not voltage or temperature compensated. So again, check out the datasheet for a bit more information about the delay range. Now, as I mentioned, the DFS, or frequency synthesizer functionality, offers the widest range of clock multiplication and division. And as I mentioned, you can select a multiplier and a divisor from a series of integers that are supportive of the DFS. In this case, the multiplier can range from 2 to 32 and the divisor from 1 to 32. And so as your imagination can think of, you can do lots of different fractional divisions and multiplications to come out with something that's most suitable to you. Now, the clock FX 180 is again a 180 phase shift relative to the clock FX, and if the clock feedback is used, the phase of the clock FX and clock in will be locked. For every M cycles of the clock FX, there will be D cycles of the clock in. The phase of the corresponding edge will be phase related according to the phase shift settings of the DCM. The clock feedback port can be left unconnected if the designer has no phase relationship desired for their application, and this can be done by setting the attribute clock feedback to none, or done with the Architecture Wizard GUI when customizing your DCM. Now, the DCM clock gen primitive provides some advanced clock management features we really haven't covered so far. It supports a dynamic programming of the frequency synthesis, so allowing the designer to actively, while the circuit's operating, change the multiplier and the divisor value dynamically if they so desire. This will support a wider range of multiplier and divisor values as well, so if you would like, you can try that out. It also supports a spread spectrum clock generation functionality, and also allows you to generate a free-running oscillator by freezing the DCM output once lock is achieved and allowing the designer to remove the input clock if they would like. Now, as an FYI, if you're going to be changing that dynamic programming of the frequency synthesis, this will be done with a SPI-like interface that we'll have a chance to look at later, and this is a very common and easy-to-use interface. The clock FX divide is the clock FX divided by integers 2, 4, 8, 16, or 32 set with the clock FX divide parameter. This will provide an improved jitter tolerance in the clock in input and a lower jitter on the clock FX output. And it does not have an external clock feedback port, so no clock deskew and no phase shifting is supported with that feature. Now, as I mentioned, if you're going to use that dynamic programming of your frequency output, this is done with a SPI-like interface. So you simply have to send command and data serially over the program data pins. So after a go command, the clock FX output will smoothly transition to the new clock frequency. So from this example, of course, you can see we load in a D value with a fixed gap and an M value with a fixed gap, and then the go command is received, and then so many clock cycles later, then we're going to actually see our new clock FX output become activated, and then the lock signal become asserted, being your clue that, okay, we've changed that new clock frequency that the customer wanted to use in our application. So all you'll need to do is execute this series of 3 commands, a load D, a load M, and then the go. And this, as I mentioned, typical of a SPI interface transaction, is easy to adopt. A gap is required between the consecutive commands. The user guide will define the required gap, which is 2 or 3 clocks typically. The lock signal will also deassert after the go command, and then will reassert after the new frequency is locked. And this lock time will depend on the magnitude of the frequency change that you're trying to program. Now, as I mentioned, there is a free-running oscillator functionality that's also available to you. So after the DCM has locked to an input clock, the DCM updates can be frozen. And this will allow the number of delay elements used to no longer be updated, so the clock FX output will continue to toggle at that correct frequency. When frozen using the freeze DCM input pin, the input clock is no longer required, so it can be disconnected, or the input clock will simply be ignored and could eventually be stopped if so desired. So this can be useful if your clock source is not from a static oscillator, such as if your clock source just simply came from a cable. Note that when the DCM updates are frozen, the DCM will not adapt to voltage or temperature changes. If the temperature or voltage change occurs after the freeze DCM signal has been inserted, the clock FX frequency can drift. Now there's also a spread spectrum functionality built into the DCM. This is with the DCM clock gen primitive. The frequency of the output will vary slowly over time between controlled limits, so this feature is useful for reducing the measured electromagnetic emissions of a system. There are several spread spectrum modes that are supported. Some are implemented internally to the DCM. Others will need an external state machine to manage the dynamic programming interface, so check the user guide. Now, a DCM output can be cascaded to a PLL to reduce the output jitter, but preserve the spread spectrum attributes of the generated clock signal. We'd also like to note that the spread spectrum feature will not be fully supported until the ISC 11.4 software release, which is actually coming up very, very soon. Spread spectrum mode is set via the spread spectrum attribute. There are a couple options here. The center spread low and the center spread high modes are done natively in the DCM. So these are the two modes we mentioned that are included and support of the silicon. Other modes will require an IP module for controlling the programmable interface. But with the center spread low and center spread high modes, it's a triangular distribution centered around the input frequency. The center spread high has a higher frequency deviation. Now, let's take a few minutes and complete our final quiz, and then we're going to wrap up the module. Now, let's wrap up this module with a relatively brief summary. First of all, there are 16 global clock networks that can span the entire Spartan-6 FPGA. There are 2 I/O clock networks driven by the BUFPLL that span each edge of the die, and these are sourced from the CMT outputs. There are also 4 I/O clock networks driven by the BUFIO2 primitives that span each half edge, and these are sourced from the global clock pins as well as the MGT port, which generates the GTP clock output. So if you're using the MGT, you can drive the BUFIO2 there as well. The BUFIO2 and the BUFPLL provide the clock and control outputs required by the I/O SerDes resources. The clock management tile, or CMT, comprises 2 DCMs and 1 PLL. The DCM clock gen primitive provides advanced clock management features that we haven't seen before at Xilinx, including a dynamic frequency synthesis, spread spectrum, and free-running oscillator behavior. There are some very useful resources available to you at support.xilinx.com. That's our technical resource webpage. The Spartan-6 user guide has been mentioned numerous times in this recorded e-learning. It describes the complete architecture in extreme detail. You might also look for a user guide that pertains directly to the clocking resources as well. These documents I just mentioned, are particularly helpful to customers and are very often referenced by them, so I would strongly encourage you to check those documents out. When you go to support.xilinx.com, you will notice that searching for documentation by device family will show you all the current documents for the selected device family, so you'll probably find other documents that you find interesting, like the programmable memory controller block. If you would like to see what other courses we offer, including the Designing with Spartan-6 FPGA course family, what other free RELs are available to you as well, you can go to the education link and find out there. I would also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices, including Spartan-6 memory and Vertex-6. You may find these especially useful if you want to learn more about the device differences, but whatever you do today, please take a second at the end of this REL and let us know what you thought. Just click on the icon on the next page and tell us what you think. Again, my name is Frank Nelson. You've been listening to the basic FPGA architecture module for Spartan-6 clocking resources. Thanks for your attention, thanks for listening, and thank you again for your business.